I disagree. And I'm not a paleontologist, so I'm speaking as what you'd call a neontologist. And one reason is that by the 1920s, 1930s, you had a number of very fine paleontologists, many of them European, who looked at things such as fossil corals or stratigraphy, or fossil mollusks and invertebrates in general, but also vertebrates. I'm speaking of men such as Otto Schindewolf. And what they found is that the fossil record, you have periods of explosive diversification, followed by maybe minor diversification with what they called stasis, and then you had extinction, and then you'd have another period of this. So they came to the conclusion that the fossil record is, as Stephen Jay Gould and Niles Eldredge would later say, highly punctuated in terms of these events. The interesting thing is that by the 1940s, 1950s, particularly in the Anglo-Saxon world, the idea came to the fore that there really is no, how would you say, evidence to the contrary, that Darwin had it right. And you had, for example, Marjorie Green. She wrote a famous essay, I think it's famous, called Two Evolutionary Theories, where she compared the empirical evidence presented by, say, Otto Schindewolf, who believed that evolution was highly punctuated. and she compared it with that of G. Gaylord Simpson, who is one of the most famous American paleontologists and, of course, a prominent follower of the modern proponent of the modern synthesis. And what she concluded was that Schindewolf was being quite true to the evidence, and that Simpson, on the other hand, was casting the fossil record through the lens of the modern synthesis. Those things that did not fit, he would give terms like quantum evolution to, which was just another fancy way of saying it's punctuated, or it's, there are these discontinuities, so to speak. She writes in that essay that, that there is this ruling passion in the modern synthesis, which is to defer, to move from the empirical evidence, that is the study of fossils, the study of morphology, the study of genetics, and then to move into the more abstract realm of population genetics, where then one can be playing with big A's and big B's and small b's, and applying various statistical finesses to get things to work. So I would say that the common textbook story, of the kind that you would read, say, in National Geographic, is that you look at the fossil record, you look at the geological evidence, and everything comports fully with the Darwinian theory of evolution. That yes, there may be some quote-unquote missing links, but these are few and far between and soon to be filled in, if not currently being filled in. However, it's long been noted that there are, in the fossil record itself, that there are periods of explosive diversification. I mean, where whole new, we would say, body plans appear within a period of just a few million years, followed by a stabilization of that body plan, and then long periods of stasis, possibly extinction after that. You see this, for example, with angious flowering plants. You see this with bony fishes. You see this notably with whales, where you have more or less quote-unquote walking whales, and then in a period of a few million years, you have fully aquatic cetaceans and a radical reorganization of the body plan. You see this also in the invertebrates, where you have just this, you have some groups, for example, like the edible shrimp you might find in the grocery store that's farmed. You have that they appeared in the Permo-Triassic or the Jurassic, and their body plan has remained essentially the same ever since. They have a lot of genetic diversity, but yet in terms of their morphological features, they appear in the fossil record and they've been with us for well over 100 million years. Well, if you look at the one diagram Darwin provided in his 1859 book, or at least in later editions of The Origin, where he doesn't have a single root, but he does have, he shows a diagram where you have types branching off, and gradually you have the appearance of genera and then families and then orders and on to what we would call phyla. The interesting thing about the fossil record is it's actually the reverse. You have your phyla appear first, where you have the major body plans, during the so-called Cambrian explosion, maybe a few of those body plans earlier. So we're speaking about half a billion years ago or so. And then you have the appearance of classes and orders, and then families and subfamilies and so on and so forth.